1.6a, optimum volume and surface area of a square-based prism. Okay, so we're going to touch on real-world applications for this. Okay, save money for packaging or wrapping an object, right? So because you want to save money on, like, say, the wrapping paper. Okay, so we're talking about less surface area. Less surface area means less heat loss in a house or apartment building. Okay, and we're going to take a look at that. And then hold the most amount of volume in a container. Okay, so greatest volume, least surface area. Okay, because if your building is tall and has a very, very large surface area versus more, what we're going to find out, more cubic, this one's going to lose way more heat. Okay, to optimize the volume of a square-based prism while minimizing the surface area, we must create a cube. Okay, so that's what it's going to be. So we took a look at what maximizes a rectangle, which was a square. Now we're going to look at what maximizes essentially a rectangular prism, and it is a square-based prism. So we're going to do length, width, height. Okay, and in this case, the length, the width, and the height are all going to be the same. Okay, so instead of calling it H for height, we're going to call it S for side. Instead of calling it L for length, we're going to call it S for side. And instead of W for width, we're going to call it S for side. And that's where we get S cubed. It's essentially, instead of length times width times height, we're saying side times side, because they're the same, times side again because they're the same, which is side cubed. Okay, now when we're taking a look at the surface area of a cube, we're looking at this right here, okay? And these are the same, so this is going to be S times S. These are the same, S times S. These are the same, S times S. Okay, so we're going to have 1, 2, 3, 4, 5, 6. 6 different sides where the area is going to be S squared. And that's where we get 6s squared. So each one of these sides is s squared for the area, and we have 6 of them. Okay, so our first question, example 1, if a square-based prism cardboard box has a volume of this, okay, so this is volume, determine the dimensions that will require the least amount of cardboard to create the box. So as soon as we see least, we know that we're going to use those optimization formulas. So we're going to go volume equals, so this is going to be side cubed, and then surface area equals 6 side squared. Okay, if they give us this and there's a cube on it, this means it's the volume. We're going to actually sub it into this side. Okay, so 500, 0, 0, 0. So 500,000 equals s cubed. So in order to get that cubed off of the s, what we actually have to do is we have to cube root both sides. So it's going to look like a square root, but instead of there being a 2, there's actually going to be a 3 there. Okay, for squared, when we square root, we actually have just like the imaginary 2, we don't write it in, but cube root, we have to write it in. Okay, so when we cube root this, the cube and the cube root go away, so we have s equals 79.37. Okay, so the dimensions are, therefore, 79.37 centimeters by 79.37 centimeters by 79.37 centimeters. Okay, it is 3 dimensions, so we need a length, a width, and a height, or in this case, a side, and a side. Okay, and now the follow-up question is, find the amount of cardboard required to make this box. So this is basically asking us for the surface area, right? The amount of cardboard. So the surface area is 679.37 squared. Okay. So when we put that into our calculators, we get 37,797.58 centimeters, and that's going to be squared because it's an area. So therefore, 37,797.58 centimeters squared of cardboard is needed. Okay, example 2. This one is going to be backwards to what we were given in example 1. In example 1, we were given the volume. So I'll write down the formula for volume, S cubed, and then the surface area is 6s squared. So we were given the volume and we had to go to surface area. This time, we're given the surface area and we actually have to go to volume. Okay? So determine the dimensions of the square-based prism with maximum volume. Okay, as soon as you see maximum, optimum, least, we're using these two equations that can be formed using, so this is what it gives us. We're going to use 5,400 centimeters squared of cardboard. Because it's a squared, this is an area. Then it asks for the volume. So we have to use this formula, okay? Divide both sides by 6. We're subbing the 5,400 into the surface area because that's what it gives us, okay? We're going to cancel those out, and when we go 5,400 divided by 6, we get 900 equals s squared, okay? Because it's a square, we do the opposite, which is square root, s equals 30. Okay, so we know the dimensions are 30 centimeters by 30 centimeters by 30 centimeters. Now, going backward, this is going to be our step 2. Our volume is going to be 30 cubed. So when we put that into our calculator, we get 27,000 centimeters cubed. Okay, therefore the volume is 27,000 centimeters cubed.